Ben McDowell, and my presentation is titled Nanotechnology, It's the Next Big Thing. I did my summer research with the PREM program at Norfolk State University. PREM stands for the Partnership for the Research and Education on Materials, and it's a collaboration effort between Norfolk State, Cornell University, University of Michigan, and Purdue University. And it's entirely funded through government and National Science Foundation grants. I chose PREM because I'm interested in physics and chemistry, and PREM is a combination of physics and chemistry, and it applies it at a practical level, which I was interested in learning about. So I'm going to give a little bit of background on what I did research on. First off, the index of refraction measures how light travels through an object. In a vacuum, the index of refraction would be 0, which light doesn't bend at all. In air, it's almost exactly 0, which is why we see very little distortion through the air. However, through other objects, such as water, the index of refraction is greater, causing a greater bend in light. That's why here you can see how the straw appears to be distorted because the index of refraction is different between the air and between the water, so it appears to be discontinuous. So what I was studying is a certain phenomenon called the bow tie geometry phenomenon. And basically what happens is when you have two gold nanotriangles at an extremely small scale, when they form this type of setup right here, it creates an electric field at the point between the two triangles, and you can use this electric field to change the index of refraction, essentially changing how light travels through the electric field by changing the index of refraction. So the way you create these nanotriangles is you have it's called a hexagonal formation of polystyrene beads, which is just small plastic beads. And when these spheres are packed together at their tightest formation, it creates the nanotriangles in between them. And when you evaporate gold onto the surface, and it fills in the triangles between the spheres, and when the spheres are removed, it leaves the gold triangles behind. And however, it's important to make sure you have the hexagonal formation seen here, because if it doesn't form perfectly, it'll slip, and you won't get the perfect triangles that you're looking for. You'll end up with rectangles or whatever. So what we were working with is how the polarity of the surface affects how those spheres align. And because we weren't working with the phenomenon itself, we were working with fabricating the nanotriangles to test the phenomenon. So basically we were treating the slide with the acid etch, which is basically just letting the slide sit in acid for an extended period, and it leaves hydroxide bonds on the surface of the slide, making the slide more polar than it normally would be. When the water is very polar, so when the slide is more polar, it creates a hydrophilic situation where the water, instead of kind of like beating up on the surface, like you might see with car wax, it would just beat up. If it's hydrophilic, it'll spread out widely. And we measure this through the contact angle. It's called the contact angle with the surface that it forms, which can be seen here. Basically, so the more hydrophilic that it is, the water will spread out more and will have a smaller contact angle. When the water beads up, it won't be as wide and will have a larger contact angle. And this is the program we use to measure it. This would be the syringe that we use to drop the water. And then it creates a video of it, but this is just a screenshot of the bubble forming. So a little bit of information on the importance of this. Basically, by changing the index of refraction, you can work with any type of optical device that involves light to try to optimize it and make it work better. So anything like lenses, solar panels, anything that you want to bend the light to do something, you can alter that to make it more efficient and do what you want easier. And also, this kind of helps understand the full implications of nanotechnology, because it's a relatively new field, and the way that it reacts with light is an important part of nanotechnology, so we just want to try to explore that more. So basically, the research question that I explored was we wanted to optimize the fabrication process, and we chose to explore how the polarity of the slide affected the bead formation. So this was the hypothesis and the null hypothesis. The hypothesis was that the acid etch with ammonium hydroxide, which is basically just an acid etch but more extreme, so it would leave more hydroxide bonds on the surface. That would create a greater polarity, smaller contact angle, and then a better bead formation. The null hypothesis was that the acid etch would have no effect, and the polarity would have no effect on how the beads formed and aligned. So basically we used two different methods to try to seat the spheres on the slide. The first would be the drop cast. You can see an example of that here. Actually, you can't see that real well, but so the drop cast, you basically drop the solution of polystyrene beads on the surface and it'll spread out. And as it dries from the outer edges towards the middle, so it brings the spheres back together, packing them in that nice monolayer that you want. The other one would be spin coating, which you can see here. Basically what a spin coater is it spins, you put the slide on this little suction thing and it spins it extremely, like many thousands of RPMs per second, and you drop the solution on the surface and it slides it off because it's moving so fast, and it leaves behind in that kind of trail the bead solution that you want to dry out. The problem with this is that it dries extremely fast because it's moving so quickly, and sometimes you get irregular lines, as you can see here. It kind of like creates those little creases, whereas this one is more uniform because you want the uniform bead alignment to create better nanotriangles. This was one of the better samples that we developed. I know it looks like there's a lot of empty spaces in here, but the areas right in here were extremely well packed, and they were a single layer, which is what you're looking for. And we created that using the drop cast. So these were my results. As you can see, the contact angle decreases with each successive acid etch, with the final acid etch making the contact angle almost less than half of the original control. The drop size diameter increased with each successive acid etch, which makes sense because it's more polar with the acid etch, it'll slide out more, creating a larger drop size. Also, the defects present seem to change as we changed what type of acid etch was used. Originally, the gap formation is basically when the beads don't line up perfectly. It's because they have like clusters and clumps, and that creates gaps in the formation. And then you can see as it moves down, you have less gaps and more just creases, which the creases is just because it's drying quickly and it's not going to be perfect. So it has some irregularities along it, but overall it's fairly good. And also the more important part is the size of the ordered area, which is what you're looking for to create the nanotriangles, was much larger in the acid etch than in the control, which is essentially we were trying to make the ordered area, so that's what we were looking for. So the conclusion of this experiment, it impacts how the bow tie geometries are created. Basically, because we're trying to optimize the process, we can now see the polar relationship between high polarity and good nanotriangle formation. And any type of future experiments in this field trying to optimize the process even further would be related to this. So I took all of the results that I had from my experiment and typed them up into a research paper, which I plan to submit to the National Journal of High School Science, pending feedback from Dr. Bonner, who is my research advisor at Norfolk State. So just kind of as a reflection on the project as a whole, the capstone project really allowed me to go back and reflect on something that was interesting to me, and it helped me kind of take what I had learned and reshape it into something new that I could work from and apply. And also, the research itself was very interesting. It was a very hands-on experience, and it was, it might seem a little bit like irrelevant, but to me it seemed very kind of like practical and just made sense. So I enjoyed that. And also, the Norfolk State gave me a research stipend, which I also enjoyed. So I'd like to give some shout-outs to Dr. Black and Dr. Bonner and the other faculty at Norfolk State for their assistance in this research opportunity. Ms. Graves for the help with the capstone project itself, and all my teachers who gave me scientific interest in this area, and also my family for their love of science and support. If you have any questions, I will be back straight in the back by the poster over there if you have any questions.